Hey everyone, thanks for coming. Andy, if you could kill your video, please. Thank you very much. Sylvan, we're recording. Welcome everyone to the first Pony Virtual Users Group. Sylvan and I were talking earlier today, and we were like, hey, if 4 people show up, it's a victory. We got 5 now, so I mean, basically it's a party. Thank you everybody for coming. We'll probably be doing these about once a month. To anybody who's watching the video later on, hopefully you enjoy it. Today, Sylvan is going to be talking some about writing generic code in Pony. This is kind of an advanced topic, lots of fun type system stuff on it. It's certainly something that I still struggle with right now. Other people are better, same amount of experience. We'll see. I'm very much looking forward to it. Sylvan, I'll turn it over to you.
Great. Awesome. First of all, can someone tell me that they can see this screen?
Yes, I can.
Brilliant. All right. So,
yes.
Excellent. So, generics are extra tricky in Pony, and the reason is because of reference capabilities. So, generics, even in a language like Java or Scala, can be a bit tricky to get the hang of, where you have constraints. And in fact, C# does a really nice job on this as well, where you can have some rather complex constraints and even relationships among constraints on type parameters. So in Pony, those relationships get even more interesting because of reference capabilities and the fact that we have viewpoint adaptation. In other words, we have the idea of a type as some other type sees it. And that's tricky for generic code. So I'm going to start with some examples on array, because array is a built-in type and has a relatively straightforward treatment of what in some ways is the simplest form of type parameter, which is an unconstrained type parameter. So for example, here it says class array A, right? And since there's no constraint on that, it means it could be anything. If we put a constraint on it, if we said array A, which must be a number, then we have a constrained type parameter, right? But in this case, it could be anything. And that means not only could it be any any type, it could be any type with any reference capability. So this could be a string val, but it could also be a string ref. It could also be a string ISO. And that's interesting because if it's isolated, there are very strong guarantees that the type system has to make about taking aliases to it and things like that. And so we're going to have to deal with every instance of this A as if it could be truly anything. And that's complex. So the first example of this I'm going to show is reading from an array with the apply function right here. And there's something quite interesting about this. So fun apply, which is the same as fun box apply because box is the default RCAP for a method, it returns an element of the array. Great, fantastic. So it returns something of type A, right? Except it doesn't. It returns something that is of type this arrow A as this sees it. And the reason for that is that a fun box can be called on a ref, a val, or a box. So it can be called on something mutable, immutable, or locally immutable. And that means the kind of A that we get out of looking in the array depends on the RCAP of the array we're looking at. So if we have an array of string ref, and the array itself is ref, then we'll get string ref out of it. We'll get mutable strings when we look at array elements. If we have an array of string ref, but the array itself is a val, then we will get string val because val sees ref as val. So that means on the same type, depending on the reference capability, we can get different types when we look inside the array. That's really important because immutability in Pony is deep, and it needs to be deep because we're using this to control concurrency. If it wasn't deep, then we could share something immutable, and if it wasn't deeply immutable, we would share a mutable state, right? And that's what we don't want to do. So that's interesting. So a counterexample of that is update. When we assign to an array, what do we do? Well, here it's always on a ref. So we're going to accept some value a, and we're going to return an a, but not just an a, it's an a hat. And hat means ephemeral. So what this means is we're going to plug this new value into the array, and we're going to return you the old value. Not only that, but because we are giving up the reference that we stored in the array, hat means we guarantee we destroyed a reference, an alias, when we hand this back to you. Now, if this is an array of string ref, that's not very interesting, because who cares? Ref doesn't really track aliasing. So a string ref hat is really the same thing as a string ref, essentially. But what if this is a string ISO? Now you have something quite fun. You have a very powerful guarantee. It says, if I replace this element in the array, I get a string ISO hat. And that means when I assign it to something, it's a string ISO, instead of becoming an alias of a string ISO, which would be a string tag, right? And that way you can extract isolated things out of this generic type. So the way that we write these signatures when we're doing generic programming on methods on the generic type is just as important as establishing a bounds and constraining that bounds. So another example of this is init. So here we want to initialize an array. We're going to create a new array, and we're going to initialize it so that all elements are the from value. And that means the type of from needs to be something not of type A, but something that will alias as type A. Now, if this is an array of 32-bit integers, an array of I32, that's not very interesting. I32 defaults to val, so an I32 val and an I32 val hat, whatever, they're interchangeable, no big deal. But again, if this is something isolated, an array of isolated or transition reference capability things, then what this says is, what would alias as ISO? And the answer is, well, nothing. And that's really important, because that little annotation means we can't initialize an array of isolated things to all point to the same value, because then they wouldn't be isolated, right? We'd have multiple aliases to the same thing. So that's really interesting. That gives us the power, again, to talk about reference capabilities in this generic way relatively simply. All right. Now, the next thing I'm going to talk about is the exclamation mark. We're going to look at clone. So this method says, I've got some array, and I'm going to return you a new array. I'm going to, it'll have the same contents, but it's a new array. And once again, we see that this is callable. It's fun clone, which means fun box clone. So we could call it on a ref, a val, or a box array and get an array back. But look at this type signature. It doesn't return an array A. It returns something much more exciting, because it needs to be an array of how this sees A, because we could call this, just like with apply, on multiple receiver RCAPs. So that's good. So we can say, all right, it'll be an array of how the current receiver sees its parameterized type. But then we have the exclamation point, bang. So it's this A bang, this arrow A bang. And the bang means whatever A aliases as. Because we're not going to remove aliases from the array that we're cloning. We're just making a new one. So if we had an array of string ISO, we can't create an array of string ISO when we clone it. We need the alias of that, which, if it were reified as string ISO, would be string tag. So we would get an array of string tag when we cloned it. That's pretty interesting. You'll see that this is returning array defaults to ref. So this is returning a mutable, a ref array, in fact, a ref hat. But that viewpoint adapted aliased type, again, lets us talk about this type parameter in a way that's generic, not just in the presence of generic types, but in the presence of generic reference capabilities. That's pretty good stuff. All right. So let's look at something even trickier. Let's look at concat. So we're going to concatenate an iterator of something. Now, this is similar to the from example. In fact, in some ways, it's exactly the same as the from example. Here, we've got something that we can iterate, and we're going to take everything in that iterator and push it onto the back of this array. We can't have an iterator of A because we're going to take an alias of it. So again, like the from example, we need an iterator of A hat. But here, instead of just saying we had some A hat, we're using that type parameter, a modified type parameter, as another type parameter in some other generic type. That lets us craft some quite powerful and powerfully generic methods without violating reference capabilities. All right, one more on array, and then we're going to move on to map and talk about constrained type parameters. So the one more I'm going to cover is find, because it's quite interesting. So in find, we're looking for some value in the array. But the interesting thing here is we're not just passing it in and saying we're looking for it by identity or we're looking for it by equality, because we want to be able to do either. Because not everything is structurally comparable. For example, you can't compare an isolated thing structurally to something else because you're not allowed to look inside it in that way, or a tag thing. So there are different ways we might want to compare things. So here we're passing in some alias of A, and we're giving a predicate function, which is a lambda type, which is what this is here. And what that's saying is we're going to pass in a lambda that allows us to compare to A bangs. Not only that, but because we can call this on lots of different reference capabilities, again, box, ref, or val, we want it as box sees A bang, so that any two of these things could be compared in any way. Now we're going to provide a default lambda that says, hey, by the way, mostly we just want to check by identity. But that can be replaced. That could be give something compared by structural quality. It could be have lots of different things. All right. That's another powerful concept when you're doing generic programming, is saying, I may not be able to directly talk about how I want to deal with things like equality and ordering and things like that, but I can provide the ability to supply a function in the form of a lambda that does what I need it to do, that provides those predicates. Okay, let's talk about Hashmap. So in Pony, a map, the default Hashmap implementation in the collections package is a quadratic probing Hashmap. So that's an array-backed structure of key-value pairs, essentially, that has some special entries in that array to indicate empty and deleted values. That's what we're seeing right here. Now, what that doesn't tell us is how in the world are we going to hash and compare those keys, right? Because if we're doing a hash map in this fashion with quadratic probing, we need to generate some hash value that tells us where in that array we're going to look, and so how we're going to start doing quadratic probing if we don't find what we're looking for, or if there is something there, how do we find out it's the right something as opposed to something that happens to be a hash collision? So in Hashmap here, you'll see that this actually has three type parameters: a k unconstrained, a v unconstrained for a key and a value, and an h, a hash function. But that is constrained. That says it has to be a hash function over k. Not only that, but your hash function has to be immutable. So we're not going to let your hash function mutate when it calculates hashes, because that would be bad. So h here is a constrained type parameter. Now, just providing that and saying, it's a hash map, and hey, user, you're going to have to plug in your hash function, that's powerful, but it's not really friendly. So we've got a couple of type aliases. The first one is the simpler one, which is map is, and that says map is a type alias that's parameterized over only two things, k and v. And what it says is that is a hash map over k and v, and we're going to plug in a specific hash function. which is hash is parameterized over k. And I'll just quickly show you the definition of hash is, which is here. And all that does is it says, hey, we're going to hash based on the identity, and we're going to do an identity comparison for equality. And hash is really useful for things like, what if you have a map of actors to something else, or anything where you're not concerned about structural equality, you're concerned about the identity of the thing itself, where object identity can be a really powerful concept. But then we also want to provide a map that is based on structural equality. Things like a map of strings to integers. You don't want that to be on the identity of the string. You want any string that has a certain content to be the same as any other string with that same content, right? So here's this type alias. And what it says is, here it's a map, and it's over two things, k and v. But k has a much more powerful, much stronger constraint. It says k must be hashable and of some readable reference capability, and it must be equatable to another k, and also with some readable reference capability. And when we have that, then we'll plug in a default hash function, which is hash eq over k. And I'll show you that implementation too. It's similarly simple. What that says is, oh, well, since we know k is hashable, when we're asked to hash it, we're going to call the hash method on it. So it can generate its hash however it needs to. And similarly, since we know that k is equatable, so it has a structural equality method, we're going to just call the structural equality method when we're asked to actually compare two things for a possible entry, whether it's a collision or whether we've actually found the item in our map. So this gives some rather extraordinarily nice power here in terms of operating generically over things that can be of any reference capability. Now we can have a map that is easy to use both for things like mapping actors to other things, or mapping integers, or mapping strings, or mapping any other structurally comparable value, all through the one interface. So let me show also some methods on map and how this k and v are used. So apply works similarly to array, where it's going to return this v because, right, it can be called, it's a fun box, so it can be called on a ref val or box receiver. Awesome. So it returns this v, viewpoint adapted type. Excellent. But look at this key. This key is interesting. This key does not demand a k. It just asks for how some box type would see an alias of k, which is a much weaker demand on what k is. And there's a really good reason to do that. Let's say you've got something that maps some isolated type to some other type. If we demanded k, we would never be able to find anything in the map, because the map is the only one that has the isolated reference to the instance. So instead, we can operate just on an alias. Not only that, how box sees it, because we know that we're never going to modify the key when we're looking it up in the hash map, because that would produce unfortunate results. So if we go back to the definition of hash eq and hash is, you can see that this all works, because in their hash functions and equality functions, they actually are only asking for box A. That's pretty good. Right. So update works very similarly to an array update. There's nothing magic there. On the other hand, you'll notice that it's different from an array in that it does demand the actual k, because now we're storing that key in the map. So there we need the real k. However, if you see remove, again, we can operate on some alias of k, and we're going to return you an ephemeral k and an ephemeral v, because we're going to remove that key value pair from the map. All right. Now I'm going to jump back to array and look at an interesting function, which is values. So one of the things we do a lot with collections, of course, is iterate over them. So values is a usual method that pony collections have that say, hey, we return an iterator over the values in this collection type. Keys is another one. Pairs is also another one where you're looking for both key and value, the key and value pairs that you're going to iterate over. But let's concentrate on values. This has an interesting type. It returns this array values type, which is an iterator, over A, not this A, but over A. But then also over something else, which is how this sees an array of A. Not how this sees A, but how this sees an array of A. And the reason for that is that the array values type is going to not copy everything out of the array in order for us to iterate over it, but just have a reference to this array. Well, look at that. How this sees array A is also the type of the receiver. Because again, we have a fun box. And when we look at the definition of array values, what it's parameterized over is some A and some array of A of some readable type. And it's not an iterator over A. It's an iterator of how B sees A. So here we have a viewpoint adapted type, but instead of being this arrow, it's how some type parameter sees some other type parameter. So that's pretty neat. So here we're storing this array of type B. And when we call apply on it, this being sugar for apply, we're going to, it would return this A as far as it's concerned. But what's this? Well, in this call, this is a B because we're calling it on underscore array. So the result of that expression is B arrow A. Now this is a particularly advanced form of viewpoint adaptation and most likely to be used if you're writing your own collection types. But it's also quite powerful and lets you build constructs that otherwise wouldn't be possible while maintaining all the concurrency safety guarantees. All right. I'm going to show one more example. We're going to go to set to do this. So a set in Pony is implemented as a map of the alias of a type to itself. You can see that here. So it's a map of A bang to A using some hash function H. And we have the similar aliases as map does, so that we can do this for identity or for structural equality. And we have some similar functions as map, like an apply that returns a this A. Or an extract that returns an A hat. Similarly, a set that only requires an A, and an unset that can operate on a box A bang. So this is a very similar pattern to the way that map works, and that makes sense. It's doing a very similar job to map. But now let's look at an arithmetic operation on a set. And when we use arithmetic operations in Pony, we're generally meaning operations that expect immutable operands. So in this case, a logical operation, an OR, that's a union of two sets. So if we're going to have a union of a set with another set that's capability secure and reference capability secure, what are we going to be able to union with? Especially if it's over both mutable and immutable sets. So the answer there is that it's over not some other hash set AH, but over how this sees a hash set AH. All right, that gives us some power already. It says we're only going to allow unioning sets of the same reference capability. Not only that, but we're going to return a new hash set, and it can't be a hash set of this A. It's got to be a hash set of this A bang, right? Because we're not removing elements from these sets. We're just creating a new set. And that means it can't be a hash set using the same hash function h. So we define a function level type parameter, k here, which is a new hash function. And it has to be a hash function over this arrow a bang, because that's what we need in order to have a hash set over this arrow a bang. Makes sense. But we're going to default it to h, because for a lot of sets, it turns out the same hash function we used over a is going to work just fine over this a bang. For example, if you have a set of string val, set of strings, a set of integers, many types, the same hash function is going to work fine. So we're going to default it to h, but allow the user to replace it if necessary. And that gives us the ability to return this new hash set over a possibly new hash function over a possibly new set type polymorphically over every possible instantiation of the set. All right. Now, I'm going to show one more set of examples, which is based on promises. And the reason I'm going to show that is because so far we've looked all at collection data types that behave in a very synchronous manner, similar to collections in languages like Java or something like that. But here, we're going to look at something that is asynchronous. So a promise is an asynchronous result. So much like in Pony, a behavior is an asynchronous method, right? It's a method call that you're not going to get a result. It's unidirectional. And when will it be run? It'll be run, but sometime in the future. A promise is an asynchronous result. It says, I expect this to either be fulfilled or possibly rejected, right? The equivalent of raising an error. But it's going to happen asynchronously. It won't happen now. It'll happen at some point. And when it does, I want to be able to attach some code to execute. Now, I'm not going to go into the exact uses of promises, but instead I'm going to address it from the point of view of generic programming. So because a promise is an actor, and because multiple listeners can pay attention to the result of a promise, we need to constrain what type of value a promise can return. So here we're going to use the interface any, which matches anything that's not a tuple, and say it has to be some shareable type, where share is sugar for the set val tag. So anything that is either a val or a tag is shareable. And what that means is we can send it in a message to any number of recipients. ISO is also sendable, but it's not shareable. You can only send it to one recipient. And that means we're going to be able to plug in any shareable type here, right? Except for tuples. That's an interesting thing we can discuss at some point. And that means when we come down to next, so if anyone is familiar with promises, next is the ability to say, I'm going to attach some code and I'm going to get back a promise, a chained promise based on how the fulfill function will transform the fulfilled value. So here, we're going to need to parameterize our call to next on some B that is any share in order to create a new promise B, because we want to return another promise. So it's got to be constrained in the same way that the constraint on promise is, since we're using it to fulfill the same type parameter. Similarly, we're going to pass a fulfill function, which is a fulfill from A to B, and a reject on B. Now, which is a reject always, defaults to reject always. You can provide anything you want. Now, the difference between these things is a fulfill function will be passed in A if a promise is successfully fulfilled and then generate a B, whereas a reject function isn't passed anything, but is still expected to generate some B in order to fulfill the next promise. Of course, it's also okay for the reject function to raise an error, in which case we'll reject the next promise. This is some interesting stuff about the way promises are chained. So what you can see here is that we've got lots of type parameters being used in lots of types all in one method. So we're not only using the A from the method, we're also using, the A from the type, we're also using the B from the method, and we're using them to parameterize multiple types: the fulfill, the reject always, and the promise. Does anyone have any questions so far? Feel free to interrupt. Okay, good. I'll just keep banging on then. Right. So one of the things I want to point out is that this is all advanced type system stuff. And a lot of times when you're going to write Pony code, you're going to sit down and you're going to write types that don't do any of this, that have no generic parameters, no formal parameters on methods, and don't let this scare you off. On the other hand, when you want to use it, this kind of expressiveness for concurrency safe generics gets really valuable really quickly. All right, so the next thing I'm going to show you is list, because list has some functional calls on it, which are quite fun. So a list is the list type in collections is a doubly linked list over A, and that means it can be over any A. And you've got some of the same stuff that you saw in array and map. We've got this from, we've got this from. Now, in this case, it's currently over array A, and we're going to change that to be over an iterator of A hat. Sorry, it's over an array A hat, and we're going to change that to be over an iterator of A hat. And you've got this apply that returns a this A, and an update, which similarly takes an A and returns an A hat. These things should be familiar at this point from array and map and set. But we also have some more interesting methods, such as map. So what map is going to do is it's going to apply a function to every element of the list and return you a new list that is the result of that function being called on every element of the list. So if you've done any functional programming, this will be really familiar. So in this case, we're going to expect some lambda that operates, again, not over A, but over this arrow A bang. And because we want a list of B, this lambda can't return a B. It has to return a B hat, because it needs to be something that when aliased is a B. And that lets us return the list B. And actually, the underlying code is really simple once you have all that, right? All we're going to do is get the head and recurse into the helper function, which is a tailed recursive function that operates over list nodes, so that you can see that here. So this just says, hey, we're going to expect a list node with that same lambda function, that same with an accumulator, in this case, beginning with an empty list B. And we're just going to apply our function to the content of the list node, push it on the end of the accumulator, and move on and make a tail recursive call onto the next list node using the same lambda and the same accumulator. And when we're done, when there are no more elements, essentially when list node next can't return because there's nothing left, we'll just return the accumulator. So this is good. This is an example of why when people ask if Pony is object-oriented or if it's a functional programming language, I tend to say yes. Capabilities lets you write these powerful functional constructs that use immutability and other such concepts to do very powerful things. We can express those with reference capabilities and generic types in a way that may look a bit object-oriented, but under the hood is actually completely functional. And you'll see that there are even things like flat map. So you provide a lambda that generates a list of B. And what we're going to do is actually concatenate those lists into a single list of B. Filter, which gives you a Boolean predicate that says, give me only the elements that satisfy this predicate. And again, you can have any arbitrary predicate. and obey the reference capabilities. Under the hood, you can do whatever you want to filter those elements on the list. And again, we have this goes on where we have most of the usual suspects when it comes to functional programming. There's fold, and there's every, and exists, and a partition, a drop, stuff that is pretty fundamental for functional programming, but can be implemented in a very straightforward way when we're using generic reference capabilities. All right. Does anyone have any questions at this point?
I have a quick question.
Sure, yeah.
All this type, the entire type system, including generics, does evaporate by the time the code gets compiled, or
that's right.
And how much of it has any sort of performance bearing? Because I remember when you fixed the byte seek iter, you mentioned something about, I couldn't quite follow the discussion, but I remember you were discussing a point where you had to sort of allocate memory for 3 possible situations and things like that.
Right. So actually, that's an excellent question. So Pony has a fully reified code generator. And that means that when you create a map of string to I32, that gets reified as a completely different type. And we actually generate different code than from a map of something to something else, right? Aardvark to dormouse or whatever it is.
Sure.
And that means that the only time that types come into play is when you're pattern matching on type. When you're saying, hey, at runtime, is this of this type? And you can do that with as or with pattern matching with a capture in a match expression. And even that is very fast. If it's on a concrete type, it's very fast indeed. It's a single comparison to the descriptor. And if you're saying, are you of some interface type, then it's still fast, but you have a binary search through the interface types that are pre-calculated and stored in the object descriptor. So it's not a question of having to go through and runtime and determine if it's a subtype. All that subtyping information is determined at compile time and compiled in, but you do have to search a list of possible types.
Right. And generics, I'm guessing, is actually one step before that, so it definitely doesn't make it past compile time.
That's right. It doesn't make it past compile time at all, exactly. And so that's sort of the point of having these fully reified types, is that we're actually generating separate code for every instance. So we get fully optimized code paths for every instance. And that has some really interesting effects. For example, if we go back to the map code, this was such a good question. Thank you. When we are supplying this hash function that we're plugging into the map and then calling it, well, it turns out that the hash function that we're going to provide is generally a primitive that knows how to do hashing, right? If we go back here, we had this primitive hash is or this primitive hash eq. And that means the compiler actually knows the hash and equality calls in advance for a particular type and will inline them. So not only is it not a performance penalty to use a generic hash function, it's actually a performance advantage. People like to use the term zero cost abstraction now. And this is an example of a zero cost abstraction where actually we're gonna inline that code because we have fully reified types at the code generator. And this goes for even things on more complex stuff on generics. Like if you're doing things with a generic type under the hood and it turns out the generic type is a concrete type when it's reified, then you won't even have a vtable lookup to do dispatch. It'll be able, because it knows a concrete type, it will actually inline calls within your reified generic type.
Okay.
Yeah, that's a really good question. Thank you.
Cool.
And in fact, while type information is visible in pattern matching, reference capabilities disappear entirely at the compile stage, and it's not even possible to extract them in pattern matching, which means that the compiler has to make sure that all the pattern matching that has to do with reference capabilities is taken care of at compile time, and it does. That all works. but that's another example of having fully reified stuff being a big help. We don't have to go and dynamically determine if something is of some reference capability. We know that statically, and we're only checking the descriptor.
Right. I learned that when I had to match on an ISO and I had to consume it. So
Indeed, yes. Absolutely. All right. Any other questions? Has anyone run into trouble writing generic code that they want to ask questions about?
I've run into plenty of trouble, but I'm not at a point where I can ask questions yet.
Totally reasonable. All right. So in that case, I'm going to ask specific questions of you guys to see if these concepts, if I did an okay job explaining them. Is everyone comfortable? Let's start with array. With the way array is parameterized on an unconstrained type parameter. Yeah? Okay. Just stop me if not, because it's hard to get everybody's agreement all at once. So just stop me if you're not. Is everyone comfortable with the way hat and bang work to talk about something that will alias as an A or is the alias of an A?
Probably.
Awesome. Probably. Okay. Probably is good. That's good. Better than no. What about this arrow as a viewpoint adaptation? Okay. Less so. Okay. So one thing about this arrow that's good to know is you'll only ever see it in box methods. So you'll only ever see it in fun box, because for every other receiver type, we know that that the method can only be called on that specific receiver type, right? That we're not interested. If it can be called on fun tag, then we're only sure the actual receiver at the call site might be something else, but there's nothing interesting we could do from knowing that because we can't read the object anyway. So you only ever see this arrow in a fun box. And basically what this arrow lets you do is, so in C++, there's this idea of const correctness, of having multiple methods, one for a const receiver and one for a non-const receiver. And the const receiver might need to return a const result and things like that. So what this arrow lets you do is write methods that are polymorphic over the receiver in the same way that C++ lets you be polymorphic over const and non-const receivers, but write it as a single method. And the power of this is the ability to say, if I have an array, I want to get the value out of it based on my view of the array. So that if I have an immutable array, I always want immutable values out. If I have a ref array, it depends on the type that went into the array. Does that make more sense?
That's where it starts to get shaky for me.
That's where it starts to get shaky. All right. If there's anything specific I can cover, please let me know. All right, now let's get to the stuff that's significantly more complicated. Who finds the array values example completely baffling? The idea of being an iterator over B arrow A.
Me.
All right. So this is, I suspect, one of the hardest things in the type system to understand, is this idea of how some unknown type sees some other unknown type. And the advantage, this array values is my favorite example of it. This is not something that's going to be used a lot, but when it's necessary, it's critical. And in this case, it's the idea that the iterator over array values can be parameterized over both mutable and immutable arrays. But that an iterator over an immutable array is a fundamentally different type than an iterator over a mutable array, in the sense that at code generation, they're going to be reified with their own code.
Sylvan.
Yeah.
So Tiffin and I were having a conversation about, I think, something kind of related to this, and I guess the question I have is, this is being done specifically in arrays. Normally this sort of thing, normally, if we were talking about an object that had some properties that, had various reference types, if you, let's see, if your receiver had, basically the reference capability of the receiver would normally control how the reference capabilities of those properties as the receiver saw it, right?
Absolutely. Yeah, definitely.
And so is it fair to say that effectively you kind of have to do this in the specific case of arrays because your array items are kind of like properties, but not exactly properties, and so this actually makes them behave in the same way you'd expect properties to behave?
So that's interesting.
Does that question make sense, or?
It does. Yeah, that totally makes sense. So actually the values in the array are definitely properties, right? The fact that they're dynamic doesn't change the fact that they're properties, right? They're fields of the array. They're just dynamic fields in a sense, right? I might have 93 of them, but they're still all things contained within the array. So if you think of it as an ownership situation, right? The array owns those things.
Okay.
And so in the same way that an object owns its fields, if that makes any sense. So here, because we're constrained on some readable array, we don't know how B sees its own fields, because we don't have a concrete reference capability for B. It's any readable reference capability. So to talk about getting a field out of that array, what's its type? Since the receiver's reference capability controls this, damn it, what is the receiver's reference capability? It's the reference capability of B. And so we can write it directly. We can say, however B sees A. So I think your example is excellent. I hope that my answer seemed like it was related to you.
Yeah, I think so.
Could you go to that just one more time?
Absolutely.
How did we jump from receiver to B?
What an excellent question. So the reason for that is that when we're iterating over the array, we're going to make this call here, the one on line 470. Now that's sugar for apply, right?
Right.
So we're going to be making a call, and underscore array is the receiver of that call, right?
Right.
So since apply is fun apply, and since that means it's a fun box apply, and since it returns this A, well, partial function, it might return this A. Now we want to substitute in and figure out, okay, from the perspective of the next method, what does this A mean, right? Because it's not the reference capability of the iterator, because we're not calling on the iterator, we're calling on array. So we need to fill that in. So what does this A transform to?
I see.
So it needs to be based on the reference capability of array. So it's how does array see A? And in that case, what is the type of array? Well, it's constrained. We know it's some array A read A. But which array A read A? Oh, well, it's B, right? We know that from up here.
Yep.
So we get to write it concretely as B A. So when we call this method, the type of this, of the return value is B A question mark. It's a partial function that returns a value of B arrow A.
Okay.
And that means, since it's the thing that we're returning, hey, look at that. That's exactly what we're returning from the next method.
Yep.
Was that helpful?
Yes.
Awesome. So yeah, that's a really good point. Is this kind of thinking about replacing the this in some method you're calling with the type of the receiver as you see it is how the type checker actually works. And funnily enough, what you should do when you need this sort of complex viewpoint adaptation. Was that helpful? Yep, maybe.
I'm hoping when I go back and watch this 2 or 3 more times that it is.
Awesome. All right. We've got a little bit of time left. If anyone has any specific questions, I'll happily answer them. Otherwise, I'm going to expand on this same point in the context of maps. Any specific questions? All right, cool. So what I'm going to do is I'm just going to show the same thing happening on a map where we're going to have an iterator over the values in the map. We're parameterized on the key, the value, the hash function, and also over some map, which is a hash map over the key, the value, and the hash function, the same ones that we're parameterized over, and has some readable capability. And as a result, we're going to be an iterator over how M sees V. And we're going to have the same thing happen here, where map index, we take a look at that one, returns how a tuple of how this sees K and how this sees V, right? If we pop back here. So if we're going to return this K, this V, then what's the type of this in this function? Well, that's how map sees K and how, and how map sees V. And that's going to let us say, okay, well, what's map? Well, if we check out line 316, it's an M, right? We know it's that M is bound to some hash map KVH read, but which one? Well, we don't know, but it's an M, so we can write MK MV. And since we're doing ._2, we're just returning the second element of the tuple, which means we're going to return MV, which, lovely, that's the type of next. And in fact, that's what makes us an iterator over MV. I like writing out the substitutions. I'm hoping that's helping people. All right.
It helps me a lot.
Okay, cool. And in fact, if we take this exact code and we look at the pairs iterator over a map, and we look at these substitutions, here, we're just doing the exact same thing, but instead of returning the second element, we're returning the whole tuple. So we're iterating over the tuple of how M sees K and how M sees V. Hey, excellent, because that's the type of this function, and map pairs is an iterator of how over tuples of how M sees K and how M sees V. So that's good. And if we have a look then at the map pairs function, hopefully this complex type signature now doesn't look so complex to you, because it's a fun pairs, great. And what does it return? Well, it's going to return a map pairs because that's the iterator, the concrete type of the iterator. And it's over a map pairs that's parameterized over on K, V, and H, the same things as our map. And since it's going to be on us, it's going to be on this arrow, hash map, KVH. Great. And in fact, the implementation is really simple. We just construct one, right? There's that whole big type, and that's just sugar for .create. And we're going to pass it ourselves. And we can do that because the create function on map pairs, well, that's map keys, but it's the same on map pairs, expects an M, which is the hash map that we're parameterized on. In this case, the type of ourself. And that lets us store it and iterate over it in the next function. All right. So we're at the end of our allotted time, but I'm happy to keep answering questions if people have them.
Me
Okay.
personally, I need to watch this 2 or 3 times and play around with like the one thing that I was trying to do that I got hung up on. And
Yeah,
it-
this is definitely advanced stuff.
yeah, I personally definitely need lots of doing and slowly working it out and figuring out why this thing worked versus that thing.
Yeah, that makes sense.
How is hash read different from box? And what is this hash read syntax, which I haven't seen before?
Oh, excellent! What an excellent question. I'm sorry I didn't cover that. Sure. So there's the concrete capabilities: ISO, tran, ref, val, box, and tag are they're like concrete types. That it's a capability where we know exactly what it is. But there are also a few of them that represent sets of possible capabilities, and I'll write them out. So there's read, which is the set of ref, val, and box, which are capabilities that you're able to read the fields of. There's also send, which is any capability you can send to another actor. There's share, which is any capability that you can send to more than one actor. There's any, which is you'll never usually see in source code because it's the default for a constraint on a type parameter. And that's literally the set of all possible capabilities. It just says, could be anything. I don't know. And there's also alias, which is available, but you're unlikely to want it. It's important under the hood for the compiler to have this set for calculating some type checking, and perhaps it would be useful to someone at some point. It's the set of capabilities that alias as themselves. So ref, val, box, and tag. So you can't read from it or write to it, but however many times you alias it, it's still the same.
So if you had an unconstrained type parameter, would you without anything specified, would it be any by default? Is that what's going on?
Yeah, exactly. Yeah.
Okay.
So the way the compiler implements it under the hood is if you have some class wombat parameterized over A and A is unconstrained, then the compiler says, oh, what you mean is that that's actually constrained by itself of any capability.
Uh-huh.
Yeah. And so it goes and it checks and it says, are you yourself? Why, yes, I am. And do you have any possible capability? Well, yes, I do. And it type checks.
Okay, thank you.
Sure, yeah. I'm not sure if you can actually write ANE as a constraint on A. I expect the compiler might complain about that.
Sylvan, somewhat related question. Can these hash types, like these groups, be used as part of pattern matching?
No, they're not supposed to be used as part of pattern matching. I believe the compiler will complain if you try and use them outside of a constraint. If it doesn't, please let me know. They should really only be used in constraints. And the reason for that is at pattern matching time, you're looking for something that you can make concrete statements about in the type system. Now, it doesn't mean that it's impossible to use them. It just means that you're going to use a type parameter to do it. So if you had some function that wanted to do that, you could say, oh, that's fine. I'm going to parameterize on some B, which is an any read. And in my pattern match where I have some X of type A, I'm going to say match X. And when X prime is a B, I'm going to do things. And now you're using hash read in a pattern matching context, but the compiler is able to fully reify that type at code generation time. Does that make sense?
Yeah, makes sense. Thanks.
Excellent.
Couldn't you just use box instead of read? I mean, a box can be a ref or a val. Why do you need read?
What a very good question. Because in a constraint, if you were to say box, it would mean box and only box.
Uh-huh.
So
Okay.
in a constraint, it's not a full subtyping relationship. If you say this is constrained over any tag, then it absolutely has to be a tag.
I see.
Not any subtype of tag. What a good question. Excellent.
Do you have generics over the return type, polymorphism over the return type, like in Haskell?
You absolutely can, and the way that that's done is, and in fact, we saw some examples of that. So, for example, here, this next is over a B arrow A, right, which is a polymorphic return type. You can also do things like actually use a type parameter. For example, here, we could say this returns B, right, which is a type parameter. And what we're going to do is we're going to say it returns X prime. And if it's not a B, then we're done, right? That's perhaps a slightly silly function, but there you go. That function is effectively equivalent to just saying X as B. But here we've got the B as a function level type parameter, and we're going to use that in the return type. Is that what you were looking for?
But I'm very new, so I'm still struggling to understand most of it.
Oh, I'm sorry. Yeah, I thought it was a good question. I just hope that I was answering you.
I have to parse. I have to take some time to parse what you wrote.
Oh yeah, fair enough. In general, if there's a type system feature in a functional language you're looking for and you don't find it in Pony, either there might be some other way to express it, or let us know, because that could be quite interesting. For example, higher kinded types, this is a bit of a digression, but higher kinded types are not directly expressible in Pony at the moment, right? There's no way to say list over something, where you're going to say, it could be anything as long as it's a list. That would mostly be useful in a constraint, where you could say that there's some class which has some constraint where of A and B, which is a list over anything, things like that. On the other hand, that's interesting, but I'm looking for more concrete use cases to help me figure out, should this be implemented? What would be the priority of this being implemented? And should the syntax look like? And so far, each time we go to write functional features that we think, oh, actually, shouldn't we need to express a higher kinded type here? It turns out you can probably do it with structural subtyping using interfaces. So far, so good. I do expect that we're going to need them at some point. Mm-hmm. Funnily enough, the type system understands them in terms of formally, but it's not exposed, and there are a few missing things in the implementation in terms of figuring out that that's what the hell you meant to type. But it's certainly a doable feature.
Cool.
All right. Any other awesome questions? Because these questions have been awesome.
Any interesting compiler features that we can use to play around with types?
In terms of,
I don't know, some expansions or something that we can see visually, or I'm just curious. I haven't.
Oh yeah, absolutely. So it does get a little bit into reading abstract syntax trees, though.
That's yeah. I think I've been able to print them and look at them every once in a while, but
yeah.
And
yeah. --ast is your friend.
Okay.
It says print out the AST, but then the other one that's really important is the pass limiter. So in main.c, you can see that you can say to it to limit the pass. Here we go. To restrict the phases. So --pass or -r. And you can say, you know what, only run this up to, and you can say...
there's a sugar. Okay, cool. Awesome.
Right. You can say, only run it up to sugar, only run it up to flattening, only run it up to expression type checking. And that will give you the AST as it's transformed at that point.
Awesome.
Yeah, that's been that originally was purely for compiler writers debugging, but it turns out that's been so incredibly useful. Oh, and actually AST package as opposed to --AST package is really useful because it says all my imported packages, please don't print out the AST for them. They are huge. I would like just the code that I'm writing to have the AST printed out. That's really useful. Okay, cool. I think that means we're pretty much done here. Thanks, everybody.
Thank you.
Thank you.
Thanks, Sylvan.
Cool.
Thanks, Sylvan.
We'll do this again soon, and I hope everybody comes along.